let me very briefly recollect what we did in the last lecture. We were thinking of a proton and a hydrogen atom approaching each other. Then we saw that there is a reduction in energy. That is what that's what our calculations said. In fact, using variation method, we found two possible states of the system. One was called Eg and the other was Eu. The energy of Eg was actually equal to HAA plus HAB divided by 1 plus S, while EU was found to be equal to HAA minus HAB divided by 1 minus S. And further, the wave functions for these two states, which we denoted by the symbol phi g and phi u, were given by and I also pointed out that if you made a plot of Eg or Eu against R, you will find the kind of curve that I have already drawn. At far away, the energy actually becomes that of a hydrogen plus a proton. In atomic units, it is actually equal to minus half in atomic units, but for convenience we took that to be equal to 0. And then what will happen is that the energy will decrease, reach a minimum and go on to increase. This is a plot of epsilon g, while if you plotted epsilon u, you will find that the energy simply goes on increasing. So, using this calculation, it is possible to find the equilibrium internuclear distance, this distance at which the energy is the minimum, and if you did the calculation, the answer that you get is actually 1.32 angstroms. Now, interestingly, it is possible to determine this curve experimentally, and if you did that, the curve would look something like this. Well, actually it is much steeper, something like that. And the minimum error occurs at 1.06 angstroms. Theoretically is 1.32 and 1.06 is the experimental answer. It is also possible to determine this energy, the energy required to dissociate the molecule. Remember, if the molecule is in this state, is in this position, and then if you supply energy from the outside, you can actually cause the molecular distance to go to infinity, which means that the molecule will dissociate, and this height can be calculated theoretically, and what you find is 1.77, whereas the experimental value of the same distance is actually 2.77 electron volts. So, this shows that our calculation is not actually great. It gives you only roughly speaking 60% of the dissociation energy, roughly. Okay. And the bond length also is not such a great thing, because the actual value is 1.06, but instead of that you get 1.32, but then it is actually possible to do better calculations. People have done it, and in fact I told you that it is also possible to solve the Schrodinger equation for this system exactly, and if you solved it exactly you will find essentially answers that coincide with the experimental values. So, you will get 2.77 as well as 1.06 if you can solve it exactly, and as I said, it can be done. But then let us look at the equilibrium geometry. Okay. So, at the equilibrium geometry we are interested in the question, why is it that there is this bond formation. Okay. Even before answering that, we can actually say, okay, there are two energy levels that we have found. One is epsilon g, and the other is, one is not epsilon but Eg, and the other is Eu. So, these two allowed states you can represent in a figure like this. As I told you yesterday, the Eg is lower and Eu is greater. Okay. Now, Eg actually represents the energy of this particular state, while Eu represents the energy of that state. Okay. Now, these are things that we will refer to as molecular orbitals, because as we will see, these are orbitals that extend throughout the molecule. So, this is a molecular orbital, that is a molecular orbital. So, we say that when the two species are brought together, the two atomic orbitals, they combine together to give molecular orbitals. So, suppose instead of saying that, suppose they did not combine, then how much would be the energy of an atomic orbital? I have told you this. The energy would be HAA. So, on the left hand side atom you have one orbital with an energy HAA, and on the right hand side also you have an atom with an the orbital, the same kind of orbital, and we said its energy is HBB. HBB is actually equal to HAA in the case of S2 plus. So, what is happening is that these two orbitals, these two atomic orbitals, they combine and give you these molecular orbitals. One is this and the other is that, and the energy of this orbital is lower, while the energy of that orbital is higher than that of the individual atomic orbitals. Okay. So, therefore, this is usual to represent by drawing figures like this. The two orbitals interact and the result is you get two new orbitals, and in the case of S2 plus, what happens is that the one electron that is there in the system sits in this bonding molecular orbital. I say that it is bonding because its energy is lower in comparison with the energies of the two atomic orbitals. So, it is advantageous for the system to form molecular orbitals, because that will lower the energy of the system. And so, because the electron sits in this orbital which is lower than either one of the atomic orbitals, there is attractive interaction between the two species, resulting in the formation of a bond. Okay. But then you will ask questions like, I mean, how does it lower the energy, and for that we have to understand the nature of these molecular orbitals. So, let us try to understand the first molecular orbital. This is the first one. So, what is it saying? It says that you take 1 as A, add to it 1 as B and multiply it by a suitable constant which will normalize the function. That is what that it says. So, if you represent the first orbital 1 as A like this, that is the pictorial representation of 1 as A, and if this is your nucleus B, it also has a similar atomic orbital which you denote as 1 as B. And remember how 1 as A and 1 as B orbitals are, they are positive everywhere. Okay. And so, if you added these two up, If you added 1s A plus 1s B, what is the result that you are going to get? Well, you will realize that in everywhere in space the wave function would have a positive value. That is the first thing, because this is positive, that also is positive, so you are just adding them up. So, the resultant orbital, which actually is something that we refer to as a molecular orbital, it will encompass both the nuclei. So, it will be something like that. And further you would realize that in the internuclear region, what is happening is that the two orbitals are added up in the, and therefore, what is the result? The result is that there is a fairly large value for the wave function in the internuclear region. So, if you combine the two atomic orbitals in this fashion, what happens is that the wave function has a large value in the internuclear region, which means that the electron density is nothing but the square of the wave function. So, the electron density is having a large value in this region. So, if you put an electron into this molecular orbital, which the molecular orbital encompasses both the nuclei, but most of the times the electron that you put in will be found in the internuclear region. A large percentage of time it will be in the internuclear region, and therefore, we say that there is an accumulation of electron density in the internuclear region, and that is nice, because if you have electron density in the internuclear region, what will happen? This nucleus is attracted towards that electron density, this also is attracted towards that electron density, and therefore, the system remains as one molecule. You can put it in a different fashion. This electron density screens that nucleus from this nucleus, and therefore, nucleus repulsion is reduced, right. So, that is how the energy of the system is lowered. The energy is lowered simply because electron density gets concentrated in the internuclear region, and that is why this orbital, which I say is the bonding molecular orbital, is having an energy which is lower than HAA. So, we refer to this orbital as the bonding orbital. On the other hand, if you think of 1s A minus 1s B, which is what you have in the case of the other orbital, right. This molecular orbital has 1s A minus 1s B multiplied by some normalization factor, some constant. So, how will I represent it? Well, this is my 1s A, and 1s B has a similar appearance, but what I have to do is I have to multiply 1s B with a negative sign and add. So, because you are multiplying by a negative by a minus 1, I will denote it with a different color. Okay. So, this is positive, while after multiplication this is negative, and then if you added the two up, what will be the result? The result will be you will have a molecular orbital which will be something like this. Here you see you will have values which are positive, while near the other nucleus you will have values which are negative. And what happens in the internuclear region? Well, in the internuclear region, if you actually think of a plane like this, suppose I think of a plane like that, what is so special about that plane? The plane which bisects the bond between the two nuclei. So, on such a plane, what will happen is that 1s A and 1s B have precisely the same value, because the distance of any point in that plane from either nucleus is the same. So, therefore, in that plane 1s A and 1s B have the same value, but you are actually subtracting 1s A from 1s B, which means that on this plane 1s A and 1s B will cancel each other exactly, so that the answer is going to be 0. Okay. And therefore, what happens right in the middle, if you think of such a plane, on this plane the wave function will be identically equal to 0. On this side of that plane the wave function will be positive, while on the other side the wave function will be negative. So, if I drew a plane like this, something like this, let me say, right, on this plane the wave function psi, wave function phi u is actually equal to 0. Now, that is not actually surprising, because this is the lowest possible state of the system. The lowest possible state has no nodes. Remember, this always happens, lowest possible state has no nodes, but this has one node, which immediately tells me that this actually represents an excited state of the system, not the ground state. It has one node. What is that node? It is a plane that bisects the bond, right, perpendicular to the bond, and at the same time cuts the bond into two equal halves. And if you put an electron into this orbital, there is no accumulation of electron density in the internuclear region. In fact, electron density actually is removed from the internuclear region, because the wave function has a node, and therefore, this orbital is not a bonding orbital. It is what is referred to as an anti-bonding orbital. Anti-bonding molecular orbital. So, this one is bonding, while that one is anti-bonding. Okay. Now, further, see, if you look, you remember 1s orbitals are actually spherically symmetric. So, I have two 1s atomic orbitals, both of which are spherically symmetric, and in the first orbital phi g, what you are doing is you are just adding them up. But if you think about them, you will realize that they have cylindrical symmetry about the internuclear axis. See, imagine the two nuclei are here. You think of an axis passing through both the nuclei, right. This is what I refer to as the internuclear axis, and these are my orbitals. Now, you would realize that if I rotated both the orbitals about this axis, the appearance is actually going to be unchanged, because they are actually having cylindrical symmetry about this axis. As a result of that, even this combination 1s A plus 1s B, if I rotated it about this axis, the appearance is actually unchanged, and therefore, people say that this is a sigma type molecular orbital, sigma type. Similarly, with the antibonding orbital, the same kind of thing happens. If you rotate this orbital about the internuclear axis, you will find that the appearance of the orbital is unchanged, and so this also is a sigma type molecular orbital. Fine. And S2 plus is a molecular ion which has a center of symmetry. Okay. So, suppose you perform the operation of inversion about the center of symmetry. What is the result? Well, how do you perform the operation of inversion? The answer is actually extremely simple. Imagine this is your molecular ion with the two nuclei, okay, and this is your bonding molecular orbital, something like that. And remember that the molecular orbital is actually completely positive everywhere, it is positive everywhere. So, to perform the operation of inversion, what you do is you think of any point in space, maybe a point somewhere here, okay, and what you do is you draw a line from that point passing through this center of the molecule. The center of the molecule is right in between these two nuclei. So, that is the center of the molecule. So, you draw such a line and then you extend that line on the other side. So, in such a fashion that this distance and that distance are the same. Okay. And then what you do is you look at the value of your function at that point and construct a new function in such a fashion that the value of the new function at that point is equal to the value of the previous function at the original point, right. So, if you did this operation with this molecular orbital, you would realize that the molecular orbital actually remains unchanged. That means, after the performing, you do it for all the points. Okay. After performing that operation, you will see that as far as this molecular orbital is concerned, okay, as far as this molecular orbital is concerned, if you perform the operation of inversion, nothing happens, the orbital remains unchanged. And therefore, people use a German word gerät to describe this orbital, which essentially means that the orbital remains unchanged as a result of this operation of inversion. So, this is actually gerät, and that is the reason why I was actually using this symbol G, right, because it is gerät. Or I can more specifically say that this is a sigma G orbital. I said it is a sigma type orbital, but now I am more specific, it is a sigma G orbital, and it has been obtained by combining together 1s A and 1s B. So, that also I will indicate and say that it is sigma G 1s orbital. Now, suppose we performed the operation of inversion with this orbital, then what you will find is that when you perform the operation of inversion, this positive region, it will go to the other side and this negative region will come to this side, and therefore, that is actually equivalent to taking the original orbital and multiplying it by -1. So, therefore, I say that this is an orbital that is antisymmetric under inversion, and we use the German word ungerät. You add an UN and say that this orbital is ungerät, and that is actually indicated by saying that this is a sigma U type molecular orbital. It is a sigma type and it is ungerät, this orbital, and it has arisen from 1s atomic orbital. So, therefore, you will say sigma U 1s, and further in addition to this orbital is actually antibonding, and antibonding orbitals usually are indicated by putting a star. So, therefore, we say now say okay, 1s A, this is my 1s A, this is my 1s B. What have they done? They have combined together, they get they give rise to a sigma G 1s orbital which is bonding and a sigma U star 1s orbital which is antibonding, and there is one electron sitting in sigma G 1s. Okay. Now, suppose by some means I have the molecular ion sitting in the lowest possible state, which means the electron is sitting here, and suppose I allow it to interact with electromagnetic radiation and it absorbs a photon. As a result of that photon absorption, this electron, let me say, is promoted to that orbital. Now, you see, if the electron was sitting there, then the system is stable. But the moment I have promoted the electron there, what will happen? There is no stability for the system, right. The system is unstable, and therefore, what will happen? Once I have promoted the electron, the molecular ion will actually dissociate. I can show that in this picture. You see, if you are starting from here and if you are exciting it to there, right, because once you change the orbital, the electron change the place of change the orbital in which the electron is sitting, the electron is promoted from this state to that state, as a result of which the molecular ion will dissociate. Okay. So, it is actually possible to cause dissociation of S2 plus because you are changing the electron from the bonding to the antibonding orbital. Now, many of these things that I have told you are available in my PowerPoint presentation. So, we will have a brief look at the PowerPoint presentation. This actually is a density plot. If you look at these, you see these are points, these two are points where the nuclei are sitting, and the surrounding things that you see are actually the values of the wave function, different values being represented by different colors, and as you go away obviously the wave function will decrease. And in the next picture I have a similar, I have a slightly different kind of representation. What is being done is I have the two nuclei in a plane, let me say in the xy plane. So, in that plane what I will do is I will evaluate the wave function at each point, right. At this point I will evaluate the wave function and show the value that you obtain along the vertical axis. And you know that these orbitals have a large value at the nucleus, as a result of which you have these two tent or these two tips sitting there. They actually are positions where the nuclei are, and as you go away from there the value of the wave function actually decreases, which is shown by that. Notice further that in the internuclear region there is a build-up of electron density, and so essentially what you would say is that you see there is constructive interference in that region, because the two atomic orbitals as you know are getting added up. So, one says that there is constructive interference in the internuclear region, and that constructive interference actually causes the electron density in the internuclear region to go up, and that results in the formation of the bond. In comparison with this, or maybe before going into that, let us look at what happens to the electron density as the two nuclei are coming together. This is an animation that I have created. You can see that the nuclei are sitting at these points where the tips of this two tents are, and as you can see you would realize that the electron density in the internuclear region is increasing as the two nuclei come together. In the animation that you have seen just now, the two nuclei start at large distance and then they come close and close, and then eventually after coming close we allow them to separate. That is actually the animation, but because the animation is looped, what you see is an appearance in which the two nuclei are oscillating. That is not actually the way the animation should be. As I said, it is just because the animation is being looped that you get the appearance that the nuclei are oscillating. All that you should look at is just one approach like that, and then one separation going away. Now, in the next figure you will see same kind of plot for the wave function for antibonding orbital. So, this is actually a density plot for antibonding orbital. This region one can say is positive, that region is negative, and right in the middle, as I have already told you, there is a nodal plane. Okay. I have one more picture showing this. This will correspond to the position of the first nucleus, while somewhere here will be the wave function for will be the position of the second nucleus, and somewhere in the middle is your node, right, and therefore you can see that the wave function has negligible value at that point, which will become clearer when I look at the electron density. Now, in this case what is happening is that you are subtracting one atomic orbital from the other, and therefore in the internuclear region you can say there is destructive interference, and so it is destructive interference which causes the electron density to be taken away, or the wave function to be taken away from the internuclear region, and that is the reason why there is no bond. In fact, this is an antibonding orbital. So, this is the wave function, an animation showing the wave function as the two nuclei approach, and in the next animation I have the electron density. And if you look at this animation, you would realize that even though the nuclei are approaching at the right in the middle, right in the center, there is no build up of electron density, and that is why this orbital is antibonding. Okay, now that actually completes my discussion of H2 plus, and I shall now think of more complex systems. Obviously, the next more complex system is hydrogen molecule. Having understood H2 plus, we should look at H2 molecule. So, as usual, we will start with the Hamiltonian for H2 molecule. Well, in the case of H2 molecule, you have two nuclei, which we will call A and B, and you have two electrons. So, electron 1, electron 2. Now, strictly speaking, when I write the Hamiltonian, I will have to include kinetic energies from the motions of both the nuclei as well as the motions of the electrons. But just as in the case of H2 plus, we will assume that nuclei may be taken to be stationary, and at different internuclear distances I can go ahead and make a calculation of just the electronic energy. So, therefore, with the Hamiltonian that I am going to write down will assume that the two nuclei are kept fixed at a particular distance, which I denote by the symbol capital R. So, then what is going to be the Hamiltonian? I shall write it in atomic units. The first term will be minus half del 1 square. This represents the kinetic energy of electron 1, right. I have put h cross m, everything equal to 1. So, therefore, the term looks very simple. Then I would have minus 1 by 2 del 2 square, representing the kinetic energy of electron 2. And then I have to worry about the interaction of electron 1 with the nucleus A, its interaction with nucleus B. So, the distance of electron 1 from nucleus A, I will call it RA1. This distance will be called RB1. That will be RA2, and this will be RB2. And of course, there is a repulsion between the electrons 1 and 2. So, naturally, this distance also is important, that I will call R12. So, the notation is actually obvious. And if you wanted to write the potential energy of the system, what will happen? I will have minus 1 by RA1. Remember, this is in atomic units, that is why it looks nice and simple. This is the attractive interaction between electron 1 and the nucleus. Similarly, you have the attractive interaction between electron 2 and nucleus A. Okay, maybe I will write it in a slightly different fashion, the same term, set of terms. I am going to write it like this: minus 1 by RA1 minus 1 by RA2. Then I would have the interaction with the nucleus B, which will be minus 1 by RB1 minus 1 by RB2, correct. And of course, you have interactions between the two electrons, which is actually 1 by R12. And what would I like to do? I would like to solve this equation, H psi is equal to E psi. And what about psi? Psi will be dependent upon the position coordinates of the first electron. It will also depend upon the position coordinates of the second electron. So, it is a function of 6 position coordinates, coordinates of the first as well as the second electron. Remember, I have not included spin, right. We can worry about spin later. And obviously, this equation simply cannot be solved, because you have, right, you have 6 coordinates, right. That means you have 6 partial differentiations. So, this is a partial differential equation involving 6 variables, and almost impossible to solve. I mean, I should not say almost, it is impossible to solve. And if you look at the problem, what is the term that makes life difficult? What is it that makes the solution of this equation impossible? The answer is that there is this 1 by R12 which tells you that the two electrons repel each other. This is the problem. This is the reason why things are difficult. Because of this term, what do the electrons do? They always try to avoid each other. That means their motion is correlated, a word that I have used earlier, and as a result of that, it is not possible to solve this equation. And if it is not possible to solve this equation, I would like to know at least what will happen in the ground state of the system. Imagine I have two hydrogen atoms and I bring them together. Would there be an attractive interaction between the two leading to the formation of a bond if the system is in the ground state? So, if I slowly imagine, I slowly bring together two hydrogen atoms, would there be a lowering of energy? That means, would a bond be formed or not? That is the kind of question that I am interested in. So, therefore, I am very much interested in the ground state of the system H2. And if you wanted to answer this a question like this, what is it that you will have to do? You will have to write down a suitable trial function phi R1 R2 for the molecule, for the system, right. And the question is, what is the most or best suitable trial function using which I can perform calculations. And there have been two sets of trial functions. One set actually is referred to as the molecular orbital approach. So, you can say phi MO, which is what I will discuss now, and the other is actually referred to as phi VB. First, I shall discuss this approach, which is referred to as the molecular orbital approach to the case of H2 molecule, and this means I am going to approximate the wave function for the actual system by some procedure which is based upon molecular orbitals. So, what is the approach or what is the basis for the approach? Let us now imagine that I take this Hamiltonian, and for this Hamiltonian I actually cannot solve the Schrodinger equation. Why is it that I cannot solve it? The answer is that there is this electron repulsion 1 by R12, that is the reason. So, imagine for a minute that this term was absent. Suppose this term is not there, okay. Maybe temporarily I will strike it off to emphasize that. Suppose I imagine that this term was not there, then what is the problem? The problem is now extremely simple. Why? Because you have two nuclei, they are stationary at some fixed distance, and you have two electrons. The electrons are moving around both the nuclei, but the two electrons are not repelling each other, because I say, okay, imagine this is not there. So, therefore, the two electrons are actually not feeling the presence of one another, but each one will feel the presence of the two nuclei, right. So, each electron will move as if it is in an H2 plus molecule, because you see the electron does not feel the presence of the other electron, but it feels only the two nuclei. So, each electron feels only the two nuclei, right. And I know what will happen. An electron which feels the presence of two nuclei will do, they will form, right. The system will form molecular orbitals, and the first electron will sit in a bonding molecular orbital of H2 plus, and similarly the second electron also I expect will sit in a bonding molecular orbital of H2 plus. So, therefore, what will be the wave function for the system? The wave function would be given by this. I will say that the first electron is sitting in a sigma g 1s orbital, because that is the bonding orbital, sigma g 1s, this is electron 1, and the second electron also is sitting in the same orbital, sigma g 1s R2. Now, to be very clear, I want to tell you what this function is. Even though I have used this as shorthand notation, this actually means I would have this, what I have written here means I would have 1 by square root of 2 into 1 plus s right, 1 as A plus 1 as B, right, that is what it means. But 1 as A itself I would like to write in a slightly more detailed form, that is actually equal to 1 by square root of pi e to the power of minus, that is the precise form of 1 as A, e to the power of minus R A, right. The constants are not there because I am using atomic units, plus 1 by square root of pi e to the power of minus R B, but here you see the R A and R B are actually for the electron 1, because electron 1 is sitting in sigma g 1 s. So, therefore, I should, strictly speaking, I should say R A 1 and R B 1. And similarly, if you thought of this, the expression is going to be similar. You are going to get 1 by square root of 2 into 1 plus s 1 by square root of pi e to the power of minus R B, sorry, R A 2, because I am concerned with the second electron, plus 1 by square root of pi e to the power of minus R B 2. So, the actual function which I mean when I write such a thing is this function. So, this is my approximate wave function. Okay. And so, what I am going to do is, you see, this is actually valid provided electron repulsion is not there, but I can use it as a trial function in my calculation. So, I take this trial function, and what will I do? I will calculate script E. How will you calculate script E? The answer is very simple. You will take this approximate function, which I denote as phi MO. It depends upon R1 and R2. I allow the Hamiltonian to operate upon it, multiply the result by phi MO star R1 R2, okay. And then you will have to integrate over d tau 1 for the first electron, d tau 2 for the second electron, and divided by integral d tau 1 d tau 2 phi star R1 R2 MO phi star R1 R2 MO. So, this is the way in which I will calculate script E. Now, this is not a simple calculation, it is quite an involved calculation. So, we will not go into the details, but it is enough for our purpose to say that okay, I know what this function is, and it is also possible for me to calculate this script E. And I can calculate the script T at different values of the internuclear distance. So, that means I can get this as a function of capital R. For each capital R, I will do this calculation, and what is the result? The result is something that I will refer to as E with a subscript MO, because this is the result of my molecular orbital approach to the wave function. So, after that you can make a plot of EMO of R against R, and if you did that, the result is actually shown here in this picture. Maybe best thing is for me to draw it on the board. Far away you have two hydrogen atoms, the energy of two hydrogen atoms. I am imagining that I bring the two together. So, actually what I would expect is that as you bring the two together, the energy will decrease. This is what you would expect. The energy would decrease, reach a minimum, and then you will expect it to increase. Why does it increase? Because the two nuclei are close together, they are going to repel each other. And experimentally you can determine the dissociation energy, this height, can also determine RE. RE is found to be 0.74 angstroms, and the dissociation energy dE, experimentally it is found to be 4.72 electron volts. Now, this particular wave function phi MO, this particular function phi MO, if you used it and calculated the value of script E, then what you find is that the curve looks something like this. Okay. Well, first of all, the thing that you notice is that the behavior of the curve is actually quite wrong, because far away when I increase the distance between the two nuclei, the energy actually should go to the energy of two hydrogen atoms, which we take to be 0, but it does not do that. So, therefore, there is some problem, but the other thing is, okay, in spite of that, if I calculated the dissociation energy by taking this energy difference. So, what is that energy difference? The energy difference is the difference between the energy of the system at equilibrium internuclear distance and the energies of two hydrogen atoms. That you can find out, you will find that it is actually 2.65 electron volts. So, you can say, okay, this is my estimate of dissociation energy, which is 2.65, and in comparison the experimental value is actually 4.72 electron volts. And you can also determine the equilibrium internuclear distance. The equilibrium internuclear distance, according to the calculation, is 0.83. Maybe I should write a table which gives you these values. This is for H2 molecule. I am using molecular orbital calculation. Here is my value of Re, here is my dissociation energy. This is found to be 0. Did I write the value? Probably not. 0.83 angstroms, the theoretical calculation. Angstroms, and dissociation energy is found to be 2.65 electron volts. In comparison, the experimental values are 0.74 angstroms and 4.72 electron volts. In addition, of course, I have pointed out that this does not describe the dissociation of the system correctly. There is some problem. Because if I calculate the energy of the dissociated system, it should coincide with the energies of two hydrogen atoms, but it does not do that. Now, again, if you compare the bond lengths, it is not actually very great, it is okay, 0.74 and 0.83, but the dissociation energy itself, you find that it is, roughly speaking, something like 55–60% of the actual value. Okay, I think I will stop here and continue in the next lecture. Thank you.